How do we construct a field of order 8? GF8, GF2 cubed. Once again, to construct this, based on things we know so far, you'd want to construct it as a factor ring of z2x by an ideal generated by some irreducible polynomial. But if we want the field to have 8 elements, we better pick that polynomial to be a cubic. What cubic? There could be a couple different choices. I think there are. Probably the simplest one is to pick x cubed plus x plus 1. It is a cubic, still degree 2 or 3. So to confirm this is a maximal ideal, all you have to do is verify that this polynomial is irreducible by showing it doesn't have a 0 in Z2. And you can just look at it. 0 is not a 0. 1 is also not a 0. You get 1 plus 1 plus 1 is 3. Mod 2 is 1, not 0. It's cubic, so we know from things we've done in the past that the coset representatives can be taken to be quadratic. Call this I. We can write the elements as ax squared plus bx plus c plus I, where a, b, and c are elements from Z2. So you got 2 choices for a, 2 choices for b, 2 choices for c, all together giving you 2 cubed, 8 elements total. I could list them out. I'm not going to. But what I am going to do is I'm effectively going to use my shorthand notation right away. And so I'm going to say let W equal, or omega equal x plus I. We have seen before that if I do make that identification, omega is x plus I, that will be a root of this irreducible polynomial in this field. Why? Do the calculation, plug it into that polynomial, omega cubed plus omega plus 1 really means x plus I cubed plus x plus I plus 1 plus I. Do those coset operations, cube this coset by cubing its representative. And I can just keep these other cosets as they are. And then add cosets by adding the representatives. Like this. But then because of what this ideal is, that gets sucked into there. This simplifies to I, which is the 0 element. We've talked about this before. That confirms this is a root of that irreducible polynomial in an extension field of Z2. That was Kroneker's theorem. So that's the key equation. Oh, that's confirming omega is a root of that polynomial. I can write omega cubed plus omega plus 1 equals 0, which is equivalent to omega cubed equals negative omega minus 1. But if we mod coefficients by 2, that's the same as omega plus 1. And that's the key equation to simplifying multiplications in this field. Omega cubed equals omega plus 1. It is also true in terms of omega that I can fairly quickly list out the elements of this field. I can write this field GF8 based on the way that I constructed it as 0, 1, omega, omega plus 1, omega squared plus 1, omega squared plus omega, and I think one more, 1, 2, 3, 4, 5, 6, 7. Yep, one more, omega squared plus omega plus 1. That is one way to think of this field. And when you multiply elements in this field to, for example, create the multiplication table for the group of non-zero elements, you want to use this key equation. Let's do what looks like it might be the hardest one. Let's, for example, square omega squared plus omega plus 1. If I square that, what do I get? So I'm multiplying omega squared plus omega plus 1 times itself. This is multiplying two trinomials, not binomials, so I can't FOIL it, but I can generalize FOIL, so to speak. For example, I can take omega squared times each element over here and get omega to the fourth plus omega cubed plus omega squared. Then I can go to the next term, omega, and multiply it times every term over here. Omega times omega squared is omega cubed, times itself is omega squared, times 1 is omega. Then I can go to the 1 and multiply it times every term. And notice how I'm lining these things up. It's kind of nice to line them up so you can add like terms more easily. I could mod by 2 right away, but I also could just go ahead and write the 2's and even a 3. Like that. But then, yes, if I mod by 2, mod coefficients by 2, this can simplify to omega to the fourth plus omega squared plus 1, mod 2. But I'm not done, because what do I do with that? It's not one of these, it seems. Well, it is. It just is in disguise. You got to simplify it. Use the fact that omega cubed is omega plus 1 to replace omega to the fourth by omega times omega plus 1. Right? If omega cubed is omega plus 1, then omega to the fourth is going to be omega times omega plus 1, which, if you expand that out, is omega squared plus omega. Omega to the fourth can get replaced by omega squared plus omega. So do it. Replace that omega to the fourth by omega squared plus omega. We're not quite done. Simplify some more. That's 2 omega squared plus omega plus 1. But then mod coefficients by 2. That's omega plus 1. Mod 2. When you square this element, you get this element, is the point. This is supposed to be, dare I say, fun. This is supposed to be the fun part of what we're doing here. Yes, it's confusing. Yes, it's weird. Yes, it's like easy to be, forget where we started with this. Where did we start? We started up here. But in a sense, it's good that we're forgetting where we started, right? This is actually in the long run a lot simpler. We don't have to write cosets every time, for one thing. It's less painful that way. We could also, I'm saying things you should be able to do for the final, try to figure out other roots of this cubic in this field extension, if there are other roots. How? This was what really got me in grad school. I was really stuck on this for my written prelims, and Nathan Gossett's dad, Eric Gossett, helped me a lot with this and said, well, why don't you just use some synthetic division, or long division for that matter, to try to find the other roots. And I didn't know you could do that. I'm like, synthetic division? Didn't I learn that in 9th grade? How is that useful? I know omega is a root. Okay? That means if I do synthetic division, where I put an omega over here, and I take the coefficients of my cubic was x cubed plus x plus 1, and put them under here, 1, 0, 1, 1. The 0 needs to be there because there's no x squared term. And do ordinary synthetic division, mod 2 with coefficients, and also, once again, using the fact that I know omega cubed plus omega plus 1 is 0, I know that. We should be able to find the other roots. Maybe. Or at least factor this initially. What do you do with synthetic division? Bring this first number down. Effectively add to the columns. Multiply omega times 1 is omega. Add 0 plus omega is omega. Multiply omega times omega is omega squared. Add, get omega squared plus 1. Multiply omega times omega squared plus 1 is omega cubed plus omega. Add these columns, get omega cubed plus omega plus 1, which I know is 0. Why? Because I already told you it was 0. That's how omega was defined effectively. It had to be, because omega is a root of the polynomial. And these things are the coefficients of a factor. This means in this field extension, E equals Z2x mod by the ideal, where the ideal was generated by x cubed plus x plus 1. I can factor x cubed plus x plus 1 as x minus omega, because omega is a root. What's the other factor? A quadratic factor with coefficients of 1, omega, and a constant term of omega squared plus 1. Okay, that's part way to helping me find another root. Could I use the quadratic formula to help me find the other two roots? That's a quadratic. Yes, you can, though it's a little weird. What should we do instead? Maybe instead we should just do some trial and error. Give this polynomial a name, call it g of x, and just try some other elements and see if they're roots. How many other elements do we have to try? Well, 0 is not a root and 1 is not a root. And we've already seen omega's root. It could be a double root. Omega could be a root of this again, so to speak, a root of this quadratic. That's possible. Is it true or not? I don't know. We have to do the trial and error and see. Let's try g of omega. Let's go ahead and see if it's a double root of the original polynomial. What's g of omega? It would be omega squared plus omega squared plus omega squared plus 1, right? Plugging in x equals omega. 3 omega squared plus 1. Mod the coefficients by 2. That's omega squared plus 1, not 0. Okay, so omega is not a double root of the original polynomial because it's not a root of this factored part. Not a root of g. How about omega squared? Replace x with omega squared. Get omega to the 4th plus omega cubed plus omega squared plus 1. But now do your fun substitutions. Omega to the 4th gets replaced by omega squared plus omega, and omega cubed gets replaced by omega plus 1. Omega squared plus omega is what you replace omega to the 4th with. And omega plus 1 is what you replace omega cubed with. Don't forget about the omega squared plus 1. Simplify. 2 omega squared plus 2 omega plus 2. Mod by 2, that's 0. Omega squared is another root. We could confirm that with synthetic division as well. So that I confirmed it just by substitution. Let's confirm it with synthetic division. Is omega squared a root of g? What are the coefficients of g? 1, omega, and omega squared plus 1. If I try confirming that omega squared is a root with synthetic division, I should get 0 at the end. The remainder. Add. 1 plus 0 is 1. Multiply. Add. Multiply. Omega squared times this is omega to the 4th plus omega cubed. Add. Get omega to the 4th plus omega cubed plus omega squared plus 1. Hey, that's the exact same thing we simplified to being 0 above, but I won't redo the calculation. But a benefit of doing the synthetic division is that I now see another factor of the original polynomial, the coefficients right there. This ultimately means f of x, which was x cubed plus x plus 1, can be factored as x minus omega, omega is a root, times x minus what's another root, omega squared is another root, times x plus, look at the coefficients here, omega squared plus omega. Now you might also argue, well, okay, what does that mean the last root is? Think about setting that equal to 0 and solving for x. If you solve it for x, you get x is negative omega squared minus omega. Which of the 8 elements in GF8 is that? I don't see any minus signs there. Well, that's because we got to mod coefficients by 2. That's the same as positive omega squared plus omega. Mod 2. You might say, well, should minus signs be here and here? The answer is they don't have to be. Omega is the same as negative omega mod 2. And omega squared is the same as negative omega squared mod 2. So in fact, I could factor f with all positive signs as well. I could write f of x, which is x cubed plus x plus 1, is x plus omega times x plus omega squared times x plus omega squared plus omega, if you just don't like having minus signs in it. What's something else you should be able to do? Find multiplicative inverses. By the way, before we do so, let's refer to that one theorem again. GF8, this field of 8 elements, as a group under addition, would be isomorphic to the external direct product of Z2 with Z2 with Z2, which would mean all non-identity elements, all non-zero elements, have order 2 under addition. Oh, yeah, that's kind of related to the fact that, if omega is negative omega, omega squared is negative omega squared. Yeah, each element is its own additive inverse. Negative omega squared minus omega is omega squared plus omega. Each element is its own additive inverse. And as a group under multiplication, the non-zero elements, take away 0, 7 left, are cyclic. A cyclic group of order 7, in fact. All those non-zero elements, well, okay. All of them except 1 are generators of the cyclic group of order 7. 1 would be the identity of the multiplicative group of non-zero elements. It's not order 7. It's not a generator, but everything else would be a generator because we know cyclic groups of order 7 have 6 generators. Group theory. How about finding multiplicative inverses as the last thing we do today? For example, we saw that omega squared plus omega plus 1 squared was omega plus 1, not 1. It's not its own multiplicative inverse. What would the multiplicative inverse of omega squared plus omega plus 1 be? Effectively, try to solve a system of equations. What can you multiply omega squared plus omega plus 1 by? Call it a times omega squared plus b times omega plus 1 to get the unity of the field, which is the identity of the group of non-zero elements. Can I solve for a, b, and c? If I can, that's going to help me find the multiplicative inverse of omega squared plus omega plus 1.
C instead of...
Yeah, plus c. Thank you. Multiply it all out. Okay, a bit of a pain. I'll do the same thing I did a few minutes ago. Omega squared times that will be a omega to the 4th. Then I'll get a b omega cubed and a c omega squared. Multiply omega times every term and get an a omega cubed plus b omega squared plus c omega. Multiply 1 times every term, I'll get an a omega squared plus b omega plus c. I don't know what a, b, and c are, so I can't really mod the coefficients, but I can replace. Well, okay, let's simplify first. A omega to the 4th plus a plus b omega cubed plus a plus b plus c omega squared plus b plus c omega. Maybe trial and error is a quicker method. Yeah, I don't know what A, B, and C are, so I can't really do any modding here. But I can replace omega to the fourth with omega squared plus, what was it? Omega squared plus omega, and omega cubed with omega plus 1. And if I do so and collect like terms, what would the omega squared term be? It comes from there, but it also comes from here. Looks like it would involve a 2a plus b plus c omega squared. I'm looking here and here when I write that, because there's an omega squared there. And that 2 can be modded by 2 to get 0. This can simplify to just a b plus c mod 2. How about the omega term? I've got an omega term there. I also have omega terms from both of these. If I combine them all, I've got an a there, another a there, no a there. I'd get a 2a. How about the b? Looking at what gets multiplied by omega, there's no b there. There is a b there times omega. There's another b there. I also get a 2b. And the c only comes from the last one here. Once again, I could mod the coefficients of these by 2 to get 0 here and here. This simplifies to c mod 2. Finally, the constant term is just c. I'm setting this all equal to 1 and trying to solve for a, b, and c. C would have to be, doesn't seem like it's going to work. Oh, I'm forgetting something. I'm forgetting another constant term coming from b times 1. It's actually a b plus c. So I effectively get a system of equations now. This is still not going to work. Where's the other a? Oh, yeah. Yep, a plus b plus c. From that a times 1. Thanks. So get a system of equations. B plus c has to be 0. C has to be 0 from the middle term. And a plus b plus c has to be 1. Okay, that's pretty easy to solve. C is 0, b is 0, a is 1. You can just look at it. So it looks like, if I've not made a mistake, that the multiplicative inverse of the original element, omega squared plus omega plus 1, must be omega squared. The a, the coefficient of omega squared is 1. The b and the c are 0, it looks like. Let's double check it by multiplication. Did this work, or did I continue making mistakes? Get omega to the fourth plus omega cubed plus omega squared. Replace omega to the fourth with omega squared plus omega. Replace omega cubed with omega plus 1. 2 omega squared plus 2 omega plus 1. Mod the coefficients by 2. Get 1. Yes, it worked.